So when should I start?
Gianluca, are you there? Because I think I was mute. So you Bruno could not hear me. I think since some of the people are in the other room for the coffee break, because we have a coffee break room, I think it's better to wait just a few minutes. And I'm asking whether Gianluca is there or somebody else that in any case will help in recording.
I'm here.
Yes, we're taking care of that.
So,
good afternoon, everybody.
So let's wait just let's say, some 4 minutes, because see now that people are joining now, so I would prefer to wait. Yes, another one and so on, so as usual. Yes, I see now that is increasing. The number of participants is growing up. Let's wait other. Yes, it's still growing. You know, sometimes it's not easy to connect and to figure out the place where to just to start the Zoom section. Yes, we're still growing the number of participants. Okay, I think in 1 minute we will start. Okay. So welcome everybody to this section. We are going to let's celebrate Bruno Courcelle. First of all, I would like to thank Bruno for accepting to give an online lecture, but not only, just a live talk. Then I would like to thank the Barry Cooper Prize Committee for the excellent work done in selecting among various nominations the winner of this year, Bruno Courcelle. So I would like to thank Anu Davar, that he's now attending the lecture, Peter Van Emdebos, we're still connected, Yuri Gurevich, and Maria Soskova. So many thanks to them for the excellent work done. Let me just say a few words about Bruno. Bruno is the first recipient of the Barry Cooper Prize of the Association Computability in Europe in 2020. He got his PhD in 1976 from the French Institute for Research in Computer Science and Automation, the famous INRIA, under the supervision of Maurice Nivat. Then he joined the Labri at the University of Bordeaux, where he remained for the rest of his career. He's an honorary member of the Institut Universitaire de France. And let me say that his nomination mentioned his monumental sequence of 16 papers written between 1990 and 2006, entitled The Monadic Second-Order Logic of Graphs. This paper culminated in the book Graph Structure and Monadic Second-Order Logic, a language theoretic approach, co-authored with Engelfried. So it's a very important book in the field of theoretical computer science. But let me add that Bruno is mainly famous for Courcelle's theorem. So theorem under his name about the study of graph algorithm. And in this framework, his theorem is mainly a statement that every graph property, which can be defined in monadic second-order logic, can be decided in linear time on graphs of bounded 3 widths. This is a very nice theorem because this theorem is able to combine second-order logic, theory of formal languages, 3D composition of graphs, to show that a wide class of algorithmic problems in graph theory have efficient solution. So I'm really honored to, at this point, to ask Bruno to start his, let's say, lecture magistralis about relational structures, monadic second-order logic, with parameters and open problems. Bruno, you are really welcome today.
Thanks a lot for your presentation. And of course, I thank the Association Computability in Europe for giving me this prize. And I am really honored to be the first one to get the prize. And I am also honored of the invitation for giving a lecture. Also, I am not so accustomed to speak to my computer, but we will try to do that anyway. So let me try to share the screen. Okay. 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 So I can start my lecture about relational structures, and the idea is to extend to relational structures a number of results about graphs. So here is a picture of Barry Cooper, who was the founder of the association. and president until 2015. Of course, you know him, but some people may not know him, so I inserted his picture on my slides. So the keywords of my lecture will be graphs, relational structure, logic, transactions, that is transformations of relational structures specified by monadic second order formulas, tree-width, clique-width, fixed parameter tractability, and decidability of logical theories. My talk will consist of 3 parts: definitions and observations, the case of graphs, so which basic results I wish to extend to relational structures, and the case of relational structure, what is happening. So first, definition. Relational structure consists of a domain and a fixed finite number of relations, each given with a specified arity. Okay, so graphs can be seen as relational structures, actually in 2 ways. The first way consists in taking the vertices as a domain, and the graph is then defined by a binary edge relation. In that case, parallel edges are not represented. An alternative description that is more powerful with respect to logical expressibility is through the incidence graph, which means that the corresponding structure will be actually a bipartite graph with vertices, the set of vertices and edges. So now each edge will be considered as an element of the domain and an incidence relation. And now one can represent parallel edges. Now, monadic second order logic. Basically, it's first order logic extended with set variables, which denotes sets. And it can express for graphs planarity, connectedness, existence of cycles, spanning trees, and even NP-complete problems like free vertex colorability and existence of a Hamiltonian cycle. Here is an example of a sentence expressing free colorability. It can be read as follows. There exist 2 sets, X and Y, representing the vertices of color 1, of color 2, and the other vertices will have color 3. And now this formula expresses the constraint of about vertex colorability. And now connectedness, or rather non-connectedness, can be expressed by the existence of a set which somehow separates the graph in 2 parts with no connection between these 2 parts. Now, for getting polynomial time model checking algorithm, it is essential to have structurings of graphs. And the 2 main types of structurings, that is of graph decompositions, are tree decompositions, giving the notion of tree width, and clique-width terms, giving the notion of clique-width. And these values, tree width, clique-width, serve as parameters for fixed parameter tractable algorithms. Both types of decompositions can be expressed in an algebraic setting by algebraic terms over graph operations that compose graphs, pairs of graphs, or transform graphs, as you will see with the example of clique-width. So tree width is well known. I just illustrate the notion with this picture, where here I have a graph. In the middle, a tree, that is the skeleton of the tree decomposition, and here the tree decomposition, where each node of the tree is actually a subgraph of the given graph. And the boxes are connected with these dotted edges, and a dotted edge links actually identical vertices, that is copies of the same vertex of the graph. So And so this is a decomposition of width 3. And okay, now cliquids are constructed in a different way, algebraically, in terms of operations. So graphs are labeled. Vertices are labeled by a number of labels, A, B, C. And a vertex, a label may label different vertices also. There is a binary operation that is disjoint union. And there are unary operations, in particular one that creates edges. I denote it add AB, which means that it augments the given graph by adding all missing edges between A and B, or if you prefer, all directed edges from A to B, if you wish to build a directed graph. And there are also vertex relabelings. So this operation, relab A into B, changes every label A into B. And there are basic graphs consisting of vertices with labels. And the cliquids of a graph is the smallest number of labels that can be used to build the graph. Of course, because we use relabelings, we can use, in many cases, a small number of labels. So here is an example of the cliques, which can be constructed recursively by adding one by one vertices, and which are linked to all previously defined vertices, you see. And so this is an interesting example because cliques have cliquids too, and unbounded tree widths. So they play in a sense the role of trees for tree widths. So there are some families of bounded cliquids, cographs, cliques, bipartite, complete bipartite graphs, trees, any class of bounded tree widths, but also there are, I would say unfortunately, many classes of unbounded cliquids like planar graphs, chordal graphs, or graphs of bounded degree. The comparison between tree widths and cliquids can be shown on these two inequalities. They show that if you have bounded tree widths for undirected or directed graph, then you have bounded cliquids, but there is an exponential jump. And this jump is not avoidable. This has been proved. So I wish to extend these notions, logic, decompositions, terms, etc., from graphs to relational structure. And I show immediately an example showing that the extension is not at all immediate, in some cases at least. So I refer to results by Specker, Blatter, and Fischer, showing that if phi is a monadic second-order sentence about graphs, for each n, I define L of phi of n is a set of simple undirected graphs whose vertices are 1 to n. And I consider the graphs which satisfies the property. And now for each integer p, I let fp of n be the remainder of the cardinality of L phi n modulo p. So this value is a number between 0 and p minus 1. And now the theorem by Blatter and Specker says that for all formulas and value p, the sequence fp of n, when n grows to the infinite, is ultimately periodic. Actually, this result, which is perhaps surprising, it is false if you define graphs with what I call MSO2 formulas, that is monadic second order formulas using edge set quantifications, or equivalently, monadic second order formulas interpreted in incidence graphs. It is also false for array relations instead of edge relation. However, it is true for relational structures of bounded degree. And there is an open problem. What about ternary relations? So I will explain later why ternary relations are quite interesting. But generally speaking, what are relational structures good for? First, you have binary structures with relations of arity at most 2. So they can express label graphs, trees, words, partial orders, algebraic terms, possibly with shared subterms, so they are called usually DAGs, Boolean circuits, and also satisfiability problems, where a problem can be represented by a bipartite directed graph that relates clauses and variables. So, of course, hypergraphs of bounded hyperedge size. They are also obviously interested in relational databases. However, 3D compositions and alternative notions are not adequate in that case, because the corresponding hypergraphs of data are essentially without structure. Actually, efficient query algorithms are obtained, but the restrictions are made on querying formulas, not on the input relational structures. Now, a few words about axiomatic geometry, because with ternary relations, one can express notions like betweenness, cyclic ordering, alignments, and triangular orientations. So, for betweenness, consider a linear order on a set N, and consider the ternary relation B of X way Z, saying that way is between X and Z. Actually, it is easy to obtain the first order axiomatization of betweenness. However, one can also consider what I call partial betweenness, that is a ternary structure N with relation A, and the question is whether A is included in the betweenness relation of some linear order. And this question is NP complete. Partial betweenness is an NP complete problem. Open question, is it monadic second order expressible? Actually, the similar properties in case of partial orders are quite easy, because one can test in polynomial time if a graph has cycles, etc., which gives rise to existence of partial orders. Another similar notion is that of cyclic ordering. So the ternary relation X way Z means that on some oriented circle, one sees X, then way, then Z. And one has also easy axiomatization and the notion of partial cyclic ordering. And it is also proved to be NP complete. And there is the same problem regarding monadic second order definability. This notion is actually useful for handling partially defined planar embeddings of graphs, where the edges incident with vertex are represented form a cyclic ordering. And we can even consider unoriented cyclic orderings, where here for array relation is necessary to express that on some orientation of a cycle, which is not fixed a priori, one sees X, then Y, then Z, then T in this order, or in another order, X, T, Z, and Y. And now alignments. Consider points in the Euclidean and oriented plane. And consider the two ternary relations. A of X, Y, Z means that X, Y, Z are on a straight line with Y between X and Z. And T of X, Y, Z means that they form a proper triangle on which we see, with respect to the orientation of the plane, X, then Y, then Z. Okay, so this is a way to axiomatize, say, in a discrete setting, geometrical properties. And there are many open problems like constructions of algebraic terms to generate appropriately these relations. Okay. So this is now the second part of my lecture about reviewing relationships between tree-widths, clique-widths, and second order logic. So here graphs are directed or not, and possibly with vertex and edge labels. I have two main classes or families of classes, tree-widths of K, the graphs of tree-widths at most K, clique-widths of K, the graph of clique-widths at most K. And I will consider the graphs obtained from trees by so-called monadic second-order transactions. I will explain a bit later. And I have two notions because I have two types of monadic second-order transactions, the basic one and the more involved one, where the transaction constructs from a tree not a graph, but the incidence graph. And the two notions are different. So a monadic second order transaction of the basic type, I do not give all technical details, selects a subset of the domain D of the input structure. So here we consider trees and define relations on D by monadic second order formulas that use the relations of the given structure. And for a set of graphs L, we have the following equivalencies. A set of graphs is included, is defined from trees by an MSO2 transaction if and only if it has bounded tree widths. A set of graphs is defined from trees by an MSOT transaction without using, without producing edges in incidence graph, then if and only if the graph has bounded clique widths. So this means that tree widths and clique widths have, in some sense, logical characterizations that are independent on particular types of decompositions and particular types of operations that construct graphs. And it is important also that we get some robustness results, because monadic second order transactions are closed under composition. So it follows that the property of a class of graphs to have bounded tree widths is preserved under MSO2 transactions. And bounded clique widths is also preserved under MSO transactions. And in this way, one can get easy proofs that certain classes of graphs have unbounded tree widths or unbounded clique widths. It is sufficient to produce a transaction mapping the corresponding graphs to some graphs known to have large tree widths or large clique widths. These two classes, MSO, say structures or graphs obtained from trees by transactions have also characterizations in terms of graph grammars. And actually, I started my work, especially with Joost Engelfried, by looking at graph grammars. And considerations about graph grammars are at the origin of the full theory. Now, let us go to a review of results about decidability. A set of graphs L has a decidable L theory, where L is a logical language that can be a monadic second-order logic or first-order logic, if you wish, if one can decide whether a formula of the language L is true in all graphs of the given set, you see. And there are 4 results saying that a set L has a decidable MSO2 theory. Then it has bounded tree widths. Conversely, if L is a set of all graphs of tree widths at most k, then it has a decidable MSO2 theory. And for click widths, there are similar results. If a set of graphs has a decidable MSO theory, then it has bounded click widths. And conversely, the set of graphs of click widths at most k has a decidable theory, where I wrote MSO plus even, because the results are proved, especially this one, for the extension of monadic second-order logic using an even cardinality set predicate, denoted even of x. The proofs we have, I obtained with Sanguilhoub, makes necessary to use that. So there is a small open problem, small perhaps difficult, remaining to eliminate this condition. Now about model checking. If phi is a monadic second order formula, then there are functions f and g, such that for every graph with n vertices, so if the graph has click width at most k, then the validity of phi can be decided in linear time in terms of the number of vertices and with a coefficient that is this function f of k, provided the graph is given by a term. Otherwise, finding the decomposition is somewhat difficult, and one needs n cubed instead of n. For MSO2, there is a similar result with tree widths, and for properties that are that can use edge-set quantifications. In that case, the decomposition can be found in linear time. So we have n here. Okay, and there are also some a converse theorem saying that provided we assume the exponential time hypothesis, if C is a class of graphs which is closed under taking some graphs, and if each MSO2 formula can be checked in polynomial time, then the tree widths of the graphs in the class are bounded in this way by an exponent of the logarithm of the number of vertices. So in a sense, to have this inequality, the n must be very large, but this shows that the link between fixed parameter tractability and tree widths, etc., works also, say, in the other direction, at least in part. Okay. Now some observation. So I mentioned 2 results. one for tree widths and one for click widths. Actually, the result for tree widths is a consequence of the result for click widths because we have the following situation. The click width of the incidence graph of a graph of tree width k is at most k plus 3 if g is undirected. And for directed graphs, we have 2k plus 4. So this means that if we know a 3D composition of the graph, then we can make it into a click width term for the incidence graph. And one can check on this incidence graph, say monadic second order formulas. And now a monadic second order formula with edge set quantification is easily translatable into a monadic second order formulas on incidence graph, you see. So actually, it is enough to prove and to use the result for click widths, and we have all corresponding results for tree widths. Of course, in general, the click widths may be exponential in the tree widths, as I said. But actually, the bound of click widths in terms of tree widths is linear in several interesting cases, like for planar graphs, for graphs of degree at most d, for incidence graphs, as shown above. So this means that the result about monadic second order logic and click widths is still usable in many interesting cases. So the two results are classically established by building finite automata on terms, but unfortunately, these automata are much too large to be implementable, and this is not avoidable, as proved by Frick and Grohe. So actually, there is a way to avoid this difficulty, and that is to use what we call, that is Irene Durand, in Labrie, and myself, fly automata. So these are finite automata that compute their transitions instead of storing them in huge tables. So if we want to handle a term with 100 nodes, if you wish, and the automata, the corresponding automata has two transitions, then we need only compute the 100 transitions that are necessary for that term. And in this way, we can make some practical computations for monadic second order properties on graphs of bounded click widths. So, and furthermore, there is also an interesting theoretical aspect that for each monadic second order formula, there is a single fly automaton that works for any graph and any click width. Because the reason actually is that all automata for the various bounds on click widths are essentially the same. They are constructed by the same scheme, you see. Okay, so this is interesting. However, we should not ignore that the construction of a click width term for a graph is a bottleneck. And actually, I said that it is easier from a tree decomposition because for tree decompositions, there are a number of algorithms that have been studied to produce tree decompositions. This is a short example to recall what is a finite automaton on terms. The example concerns arithmetic expression and the type checking of the arithmetic expression, where the types is either real or integer. And there is a table saying, for instance, that if you take the quotient of two integers, you reach a real number. On the contrary, if you round a real number, then you get an integer result, etc. So the bottom-up computation is perhaps the smallest example of a meaningful tree automaton. And for monadic second-order logic, we have the same type of automata, where the operations are disjoint union and addition of edges, etc., but with incredibly many states. So here is what I call the MSO meta theorem through fly automaton, given monadic second order formula. One can give it to a constructor of fly automata that will produce an automaton here. And now, given the graph, we give it to a graph analyzer that gives a term, possibly of a very large click-width, but it will work. And the automaton will produce the result yes or no. So we have a single infinite fly automaton, but of course, we do not obtain a linear time algorithm, because the time taken by the automaton to check the tree is not linear in the size of the graph, because it depends on the click-width and the click-width. So I do not claim that we gain a lot in terms of size of automata. Simply, the interest is that the automaton is computed on the fly and not stored in a huge table. One can do a bit more. One can, for instance, compute the number of tuples satisfying monadic second order formulas. For instance, one can count the number of free colorings of the graph. We can compute the spectrum, that is the set of tuples of cardinalities of the components of the tuples that satisfy P of X. So I repeat, the set of tuples of cardinalities of the components of the tuples that satisfy a property, or the minimum cardinality of a set X satisfying a property. And other optimal values can be computed. In which way? Because the basic fly automaton can be adapted to computation of the number of satisfying tuples, etc., etc. You may ask questions about first-order model checking. Actually, there are also parameter tractable algorithms and very active research in this field that presently gives results for so-called nowhere dense classes, and also independently for dense classes that have bounded twin widths. So this is a very new notion. Okay, and I point out that the methods for these results are completely different of those for monadic second-order logic. Why? I cannot say exactly why, but this is the situation. Now, relational structures. How can one extend these results? So, relational structures are based on a signature, say a set of relation symbols given with arity. So first, there is an easy method consisting of using some kind of incidence graphs. That is, given a structure, one makes each tuple belonging to a relation into a new vertex labeled in some way to indicate that it corresponds to relation Ri, and that it corresponds to vertices or to xj from j to n, etc. So this is just the obvious extension of the notion of incidence graph, where the relation is binary. And we have the notion of MSO2 property, and MSO2 properties allow quantifications on set of tuples. And actually, all the results for tree width and 3D composition and MSO2 logic extend smoothly to this situation. You see, so because actually there are some translations between structures and graphs, so it works easily. And we have also the result that if a set of relational structures of a fixed signature has a decidable MSO2 theory, then it has bounded tree widths. So this by reduction to the case of graphs. Another point is that for sparse structures, that is for those which have a linear number of tuples, linear in terms of the number of vertices, then MSO2 formulas are no more powerful than MSO1. So we have a class of, for sparse structures, the MSO2 theory works well. So now the difficulties come with MSO logic and without using this trick. So I will take only the example of one ternary relation as for partial betweenness, and it is enough to see the difficulties. Conjecture. If a set of R structures has a decidable CMSO theory, then it is included in the image of a set of trees under some MSO transduction. So this extends the result I had with for graphs having a decidable MSO theory plus an even cardinality set predicate. So here I make the conjecture for counting monadic second order logic, where we have a set cardinality predicate for each integer p. Okay. So now, especially regarding model checking, what should be the click width of a relational structure? And on which type of decomposition tree or terms should it be based? Actually, I would like to have the following four properties. First, I wish that bounded tree width implies bounded width in the new sense. Second, I would like to have a polynomial time construction of a term approximating this width, something similar to the cubic algorithm for click width given by Lineni and Property 3, I would like that MSO properties can be checked by fixed parameter tractable algorithm parameterized by the width, assuming that the structures are given by an algebraic expression. So I separate the problem of checking with the problem of parsing, if you wish. And last property, I would like to have the following equivalence, that a set of structures is included in the image of trees under a monadic second order transduction if and only if it has bounded width. And this would imply the robustness of the corresponding notion of width, because monadic second order transductions are closed under composition. And the conjecture that is here associated with property P4 would imply that if L has a decidable CMSO theory, then it has bounded width in this sense. Okay. Now I discussed some possible extensions of clique width and taken the example of ternary relations, equivalently of directed loop-free hypergraphs. So there is a first natural extension consisting in using the operation of disjoint union, and of course using vertex labels as for clique width. And then one could imagine to add a triple to a relation R. We can add a triple X with Z if the vertices X with Z are different and labeled by A, B, C. And this would be defined by the unary operation add R, A, B, C, extending the addition of edges on the basis of vertex labels. And the corresponding notion that we call the relation width in the book with Engelfried would be defined by minimizing the number of labels used in an algebraic term. However, this notion is far from what we want. Property P1 is false. That is, bounded tree width does not imply bounded width in this sense. However, there is a small result that if the structure has a path width k, then it has relation width k plus 1. Property 3 is true. That is the construction of a fly automaton for verification of a monadic second order sentence on graphs of bounded widths given by their decomposition. So the extension is straightforward. P4 is false because P1 is false. P2, that is the construction in polynomial time of a term optimal or an approximation of it is open, and constructing an optimal term is not possible unless P equal NP, because this is known for clique widths already. See? So this is not the best possible definition. A better definition can be defined in this way. The idea is that a free array hyperedge can be defined from one vertex and one temporary labeled directed edge. So for clique widths, we have operations that construct edges from two vertices. Here, the idea would be to construct hyperedges from different vertices and also edges. So we could propose to define the edge labels, say EQR, vertex label, ABC, and a typical hyperedge operation creating hyperedges could be this one. Add R in terms of AP, that is, we add a triple X with Z. If X has label A, and there is somewhere an edge from way to Z with label P. You see? So in a sense, the edge is can be used to make a larger hyperedge. And in this definition, edges can be relabeled and deleted, so they are temporary. And they are created from labeled vertices as in Clickwid's terms. And in that case, we have P4, and it implies P1. We have the construction, the P3, that is the construction of automaton. It can be proved directly, or it can be derived from P4. And P2 is an open problem. P2 is what? I do not remember. The construction of a decomposition in polynomial time. Okay. The general situation is that for defining relations of variety M, one can do a similar thing by using vertex labels and auxiliary relations of variety at most M-1. So this is a result that I have obtained with Hakim, Bloom, and Zat. And so in this way, one get a notion of Clickwid's for relational structures of variety M. Obviously, it is a bit complicated to use because you have many operations. Okay. Conclusion. There are intimate relationships between monadic second-order logic, Clickwid's and Clickwid's. In particular, transductions from trees provide model theoretic characterizations of these complexity measures of graphs. And we get a robustness result, that is preservation of bounded tree widths under monadic second-order transductions. Fly automata, they are implemented in a software called TRAG, that is publicly usable from this link. Okay, and okay, so it implements some decompositions of graphs, verifications of standard results like colorability problems, counting the number of colorings, of course, for graphs which are not too large and properties that are not too complicated. Okay, and there is even a tool that builds automatically an automaton from monadic second-order sentence. So it works on some small examples like checking if a graph is bipartite or things like that. So do not try to use it for formulas with a large number of quantifier alternations. Okay. Okay, so thank you for listening.
Thank you, Bruno. I ask the host organizer if they can open the audio so that we can just thank you for the nice talk.
Thank you very much. Yes.
I don't know, let us try.